So today we are going to cover the last topic of this chapter, the vibration, isolation, and rotating unbalance. And you can see there is a very good example in our household, like a laundry machine, washer. So you see a drum. So if I share with you, so what happens? You see, it's just like the washer here, which has a mass M. So the mass of washer is big M, and the mass of the rotating drum, which is small m. So this mass has a radius of, we call it as a eccentricity. So the distance r from the center of the rotation to the mass, unbalanced mass, is known as eccentricity, which is represented by the letter R. So, and then omega R is the rotation, per constant rotation. Omega R is the rotation of that drum or the rotating mass inside the machine. So the when the mass rotates, when this mass rotates, the machine starts. Let me. The machine starts moving up and down or vibrating with the rotation. So, and as you know that the force transmissibility, the force due to this mass. So, do you remember force equal to mass times acceleration? Everybody knows this equation, correct? So, what is the centripetal acceleration? So, if there is a rotating mass, omega sub r, this is r. So, centripetal acceleration is also known as a v square over r, or v is the tangential speed, which can be written in terms of omega by this, like big R omega. V equals to big R omega. And if you want to take the square of this, you'll get R square omega square, and you can plug it in. I will just put this one as big R. So a normal acceleration or the centripetal acceleration is v square, or r, I would say r square divided by r. Now we know that the force due to this unbalanced mass can be written as mass times acceleration, r omega r square. So this is the unbalanced force. Let me grab this one. The force transmitted to the foundation can be written as this equation. When this machine moves, so the mass moves like a washer, and this machine starts vibrating with a degree of freedom x, and this vibration also starts moving the foundation with a certain amplitude. I'm concerned more about the force transmitted through the, so the force due to the spring is k times x. So if I want to show, this is the transmitted force to the foundation due to the rotating unbalance. So some people, they can notice that if you have a washer in their second floor, and when the machine completes its last cycle of laundry, so it vibrates very, very fast, and that vibration can be felt in our floor. If you can feel that one, this is going to the foundation. That foundation, how much is that vibration transmitted from the rotating mass? So this is Ft over F. This is also known as T sub F. T is the transmitted force to the foundation. And what is that formula equals to? So let me show you this equation here. This is the force, unbalanced force And then if I do the equation, which you is going a little bit about the math, but I will show you the final result because derivation requires me a lot of time. But we have done this transmissibility of um, from x over f can be written like this, and then you plug in terms of frequency domain. I want to cut short this mm, derivation and going to the formula. So let me write down the final formula for the this equation. Yes, transmissibility. This is known as the. I'm gonna show you force transmissibility first. That the transmitted force to the foundation can be found by using this formula, where R equals to speeding frequency over the resonance frequency. So this is my R, and zeta everybody knows that this is equals to the ratio of the actual damping to the critical damping. And sometimes you write down critical damping as 2 square root mk or 2m omega n. These are the same thing. So this is the formula which you need for solving. And what is transmitted force? You already know that we already know this transmitted force which is given, and I can find out in terms of force. So let me write down the final answer. So if you cross multiply this force, which is the force due to the unbalance over here to the right hand side, this is the force unbalance, mr omega square, which we just started the lecture from. So use this is the unbalanced force. Now what is the this is the formula for the transmissibility of force. Please write it down in your notes. I'm going to solve some examples for your help to understand the concept. Now the next formula which I want to share with you is the what we call the displacement transmissibility. I will say this is the displacement over the transmitted force. So let me show you this formula here. This formula here, I can show you. Yes, this is the amplitude of the foundation. So amplitude can be found using the same formula from here. You see, I would say, let me grab this one here, and then I can put this over here. So these are the two formulae. So let us solve one problem. 4.23. Again, your quiz, do you want me to open it tonight, midnight, or early morning, like 7 a.m. till midnight? What do you suggest me? It's no problem for me.
7 a.m. to midnight is fine.
Okay, tomorrow it will be open at 7 a.m. till midnight. So that you have plenty of time. Some people go to work because master students are not like undergraduates. People are having some work, so I want to accommodate them. So let us solve this problem. a certain motor is started, it is noticed that its supporting frame begins to resonate at the motor speed. So resonance is occurring at, I would say, 2 pi. Let's convert it into radians. 2 pi n over 60. When you multiply, and this is n, okay, n is a resonance rpm, so 2 pi over 60, it gives you the answer in radians per second. And if you do the math, you should get, let me do the math for you, you can verify it. 2 times pi times 900 divided by 60, I got 94.25 radians per second. At the operating speed. So this operating speed is the one which I showed you. R is, this is this omega, which is the operating speed of the rotating machine, correct? So omega can be written like 2 pi operating speed, I would say NO over 60, which is 1750. Can you help your professor? What is the R? R value here now. So if I do the math without, because 2 pi over 60 is constant, so I can write down 1750 divided by 900. And if you do the math here, about 1.95, okay? Let's write it down here, 1.95. Now it says the support oscillates with an amplitude. So you see the amplitude is given. This thing is given. The amplitude of the support is 8 millimeters. So or I can convert it into meters. Agreed? And determine the amplitude that would result 1750 RPM if the support were replaced with one having one half the stiffness. So the question is, if you replace this spring, which is now like a K by 2, there is no damper in it. In this specific case, it has not mentioned any zeta value, neither C value, so there is no damper involved in it. So zeta, so in this case, I would say the zeta would be, where is this zeta? Zeta would be 0. Yes, so I'm gonna share with you this formula here. Let me grab the formula sheet for you to solve this question. This is table 4.4-1 for rotating unbalance. So we need this formula. So x equals to, I will say plus 0 because there is no um, damper involved in it. So can I write down like this, the new formula here? So mr over big M r square, and in terms of mod, because this can be positive or negative, because square converts every negative to positive, so I wanted to keep this in the in terms of mods. So, and then what the question is, so this new spring is 1/2, keeping the same amplitude. Sorry, the same RPM. What is the new amplitude? So if you replace the spring by a little bit, what we call smaller stiffness. So what will be the new displacement to the foundation? So so X you have to find out when replaced. So what will happen? Omega n equals square root k over m. So equals to, I would say it's not equal, that means k equals to m, where k equivalent equals to k over 2. So what will happen to r? R is n rotating divided by n natural frequency, which is 17. Oh, 1 second. What is this? We already found this R value here. 1.94, correct? But let me show you. If you have k over 2 here inside this, R equals omega over omega n. If you have omega over omega n, k over, I would not say it's that's just 2, k by 2 m. This square root 2 will go in the numerator. So I'm going to write down here, R, new R would be square root 2 to the old, I would say R new with the OR. When you replace the stiffness of the spring with a softer spring, then the new R, I would say new R will be written like square root 2R. So if you plug in this equation, the new R over here, I don't want to write down n over here. I'm going to write down as a new formula here. Then you can find out new. So this thing is not given directly. If you see in the question, they don't talk about the mass of the rotating unbalance. They don't talk about the mass of the machine. They don't talk about the eccentricity. But you see, if I keep as a scalar value like one variable, this ratio will not change. Okay. Or you can change. So if you find this variable like a, suppose if it is a, what is a in terms of from this formula? If you find out a equal to x times 1 minus r square over r square. Agreed? So let's plug it in. Let me write it down here. So what is my a? A equals 8 into 10 to the negative 3, 1 minus 1.94 divided by 1.94 square. So if you solve for this, do you get this answer? This is my A. A is nothing but we have assumed that this scalar value is equal to A. So let me check it in my computer. So 8 negative 3 times 1 minus 1.94 square. Since it's a mod, so you have to take the positive value. So if you place this 1, 2, 3, so you get, we will assume positive value is taken. So now let's plug it in. over here in the same formula. I'm going to use the same formula. X equals to A R square Rn square Rn square. So let's see. I'm going to use this now. Formula. What is my new X? So if I write down 5.8, let's say 88 into 10 to the negative 3. Rn is square root 2 times 1.94. So if I do the math here, square root 2 times 1.94, 2.75. So this new value becomes equal to, so let's do the math here, 5.88 e to the negative 3 times 7475. Oh, I'm sorry. I should have subtracted this. One second. This is wrong because this is 1 minus r. So I have to do the subtraction. You can verify this with me if I make some error mistakes here. So let me write down here 5.88 e to the negative 3 times 2.75. Let's say 75 square whole divided by 1 minus 2.75 square. That is equal to, yes. The displacement is in the mod, so I'm gonna write down this answer like 6. This is in meters, okay? So I will say 6.7776 millimeters, correct? So when R value increases, then amplitude of the foundation decreases. So we have proved it. When you go home, you do this problem again, okay? I will upload this video lecture for your help. Any question? Let's do another problem. I think this problem you can solve. This is similar to the previous one. I want to skip this one for your preparation, but you will do this at home. Let's do the next one. The next one is different, little bit different. It's still unbalanced. These are the problems from the unbalanced section. One of the students pointed out that I did not cover, so I thought I should cover it. And a certain pump has a mass. So the you see the mass of the pump is the big M, correct? And has a rotating unbalanced. The unbalanced weighs. So the small w, I would say is just write down W U, which is zero point 0.2 newtons. This is little blurry, but this is 0.2 newtons. This is the unbalanced weight, not the mass. Can you find out M? Yes, you can. Look, zero point 0.2 divided by 9.8. Let's find it out right now so that we can use it in our problem is 0.0204. So this is my in kilograms. Okay, this is in kilograms. The eccentricity. So if you go back to the picture, the eccentricity uh, is given like this is from the center axis of rotation to the mass. So R is given like 2.5 millimeters, or in meters it is 2.5, and the pump rotates at 1000 rpm. So the rotation speed is 1000 rpm. Its vibration isolator has a stiffness. So vibration isolator has a stiffness 73 under Newton per meter. Compute the force. Now it is the force transmissibility. So you have to find out the transmitted force to the foundation. If the isolation damping is 0 zeta, let's do with one case zeta, and the other case you will do at home. Okay, let's do with one case that you have to find out the transmitted force to the foundation when zeta equals 2.05. So let's find out the formula. Let's go to the formula sheet here. And I would suggest you keep your formula sheet handy when you're taking the exam so that you should not waste time finding out the formula from this one. So we need this formula, okay? So transmitted force transmissibility equals to transmitted force divided by the um, I would say F, but F, F equals to M R omega squared. Okay, now that is equal to, can you find out what is F equals to? F equals to 0.0204, R equals to 2.5. Let me move up a little bit to show you. R, it is 2.5, and omega R, let's find out omega R, and R is 1000. So I can write down here, this is my omega square. This is my omega square. So if you do the math, do you get 0.558? Let me verify. I got 0.559, 0.558 or 9. It's almost the same. So this is in newtons. Okay. Now this F has been found, which is over here. And let's plug it in, or let's use this formula here. So I can write on F sub T equals to 0.558. Let's plug in the values here. 1 plus 4 times zeta for A is 0.05. 0.05. 0.05 square. What is R? We have not found it yet, but we can find it now. R is equal to the ratio of the speeding frequency or rotating frequency to the resonance frequency. And resonance frequency can be found using square root k over m. Do we have the stiffness? Yes, we have the stiffness value 7300 and the mass of the pump is 23. What do you get? Can you open your scientific calculators? And in the meantime, I will do the math. Omega r is 2pi 1000 over 60. What do you guys get for omega r? And if you do the math, r, do you get r equals to 5.877? This is the frequency ratio. So like, yes, one student says yes. So let's plug it in zeta. R is 5.877 for square. This is also square. I'm just looking at this formula. Now, if you do the math, you should get the answer for A transmitted equals to 0.93. Similarly, I haven't solved for B, but you can solve it at home. The transmitted force would be a little bit bigger when zeta value is 0.7. This is for zeta is 0.05. This is for zeta equals to 0.7. The force transmitted is little bit greater because the damper, if it is heavy damper, and the force transmitted for formula is kx plus cx dot. So the larger the damping coefficient, larger will be the transmitted force. That makes sense, correct? So with that, I have covered most of the problems. So I will suggest you go over to this section for as well as the all the problems from 1 to 30. Try to see the lecture notes for more focus on the lecture problems and remaining problems, homework problem. You can see the similar problem, but I don't suggest you to keep the solution in front of you, but you can open the book to see the formula. So let's go to the next chapter. The next chapter is about more about the um, Laplace transformation. So I have shared with you the notes for the Laplace transformation. So let me share with you. And I'm going to cover this from another book. It is to how to find out the forced response. So I uploaded these notes. So can you find out these notes on your D2L? The Laplace transform. Let me make sure you have these notes available. If you go to the contents list, let me make myself as a student to see in contents, syllabus, chapters, and then Laplace trans, chapter 5. And I have made quite a lot of videos. You see, most of the problems I have solved, but I will, they are in a different server, like university have their own YouTube channel. They're not, they don't call it as YouTube, they call it a media space. So initially I made the lectures for the media space. For example, let's look at this problem. Can you guys see my screen? Oh no, they cannot see. Let me share with them the whole screen. So this is, we are trying to find. This server is a little bit slow, but let's see. So I will try to solve these problems, some of them here, but I will upload the YouTube video. I will just download from the media space to upload because sometimes it is difficult. 25, which is the last question of this. You should think about the physical, the mass is, and the right hand side, and on the left. So I don't want to completely run the video. I just wanted to show you that I have made how many videos? Like about, I think for each problem I have made some video. This is chapter 2, so I think it's good. Do you want me to share these video lectures with you? So and then the homework for the Laplace, we will solve here the problems here today, but I would suggest you when you go home, see the videos. They will help you how to solve the Laplace transform. Some people they took the Laplace transform class in the past, but they forgot. So let's do one problem here. I would say let's study what is Laplace transform here. So chapter 5. So I will finish in this week. I will complete this chapter 5, Laplace transform. So your test will be given not this weekend, but the following weekend, which will cover chapter 4 and chapter 5, which is actually the Laplace transform chapter. And there are probably 20 questions from this chapter. And I have made a few videos which you can watch. So this weekend there will be, you can focus on the research paper and try to finish some. Do you want me to extend the deadline? The deadline is just for having the space holders. It's not a complete paper. You remember, I have given you quite a lot of time till the end of the semester. So I will try to revise as the time passes by. You can put some paragraphs in the methodology section, in the results section. If you have more knowledge, you can put more knowledge into this that you can modify, edit it later down the road for submitting the final report to get the good percentage of your grades. So this is the formula for the Laplace transform. Please write it down.
Professor, quick question about the project paper. Is it okay if we just complete the first section, which I think is introduction, or do you want pieces of each?
Um, Introduction should be comprehensive, and the remaining portion you can just add or do not want to add. It's up to you.
Okay, all right, thanks.
Because I will give you more time. We still are in October, maybe 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 in the beginning of October you should see some results coming, because students are still trying to find out. And I will share some papers, because your paper, if it is good, I will publish. I will try to get it published to some journal. Don't go beyond 12 pages, I will say. Okay. I will reduce once the paper comes, because they charge more money. If the journal paper is accepted, they charge more money. So I will try to submit it to ASME or journals, such journals which have some small number of pages. They still accept the paper without the cost. All right, so let's go over to this formula. This formula is here. So I want to share with you the Laplace inverse. How do you take the Laplace inverse? Let me show you. From time domain to the frequency domain. And Laplace is like a frequency domain. Why am I saying that? You know that you have taken this lecture, I believe lecture 4. Yes. You see, this is Laplace domain, but it's actually telling you, this is very blurry, but I show you this picture is telling you that this is the imaginary axis and this is the real axis. And if this is a complex root, S1 is located here. You see, if you have studied that if the right hand side, the poles are these are the roots of the characteristic equation. And if these roots, if R is positive, if R is positive, then the response will be unbalanced. The system will not come back to the mean position. But you see, every system, if there is on the left hand side, LHS, if the poles are located on the left hand side, you see, every mass system or mass, they are coming to the mean position, maybe new mean position. So imagine this is zero, which is the suppose the mass and the damper, and this is the mass come back to them. If you just pull it here and leave it, like over here, like maybe 2 centimeter initial condition, and leave it over there, it will come back to zero after some oscillations. Okay, so the main thing is, if you know the Laplace transform, then you can find out the inverse Laplace transform to find out the displacement behavior. Is it a unbalanced system, like over here? Like if it is uh, growing, or if it is like this is unbalanced, unstable, I would say, unstable system. This is e to the positive value. So let me show you another. Some of the Laplace transforms are given in the book. I want to throw some formula. Keep writing down the formula. They will gonna help you. So if you want to take how would you take the Laplace transform of this function a e to the negative at? So I showed you the formula here, which is this function, which is f of t into the negative st times dt. And this limit, lower limit is 0, upper limit is infinity. You take the integration. Suppose this is f of s. Then if you do the math here, e to the negative s plus alpha. This is alpha, by the way. This is alpha. Let me rewrite here. This was it. So if you take the integration of this, so what do you get? So e to the negative s plus alpha over negative s plus alpha. Agree? This is how you do the integration. A is outside. So this is the integration of that part, correct? Is it t? I forgot to write down t here. So if you plug in upper limit in place of t, so if you plug in e to the negative, let me bring it as plus alpha here, minus e to the 0, correct? So e to the negative is 1 over infinity, which is 0. So I would write down here 0 minus e to the 0. Anything exponent 0 is 1, correct? So it is 1. And this negative sign is multiplied by this. So you are left with Laplace. The new function is a over s plus alpha. So you see, so if you want to take the Laplace transform of this function, t was it a, sorry, a to negative alpha t. Suppose if you have Laplace, if you want to find out the Laplace transform of a step function, and you would see the answer is a over s. But how will you prove it? The answer is a over s. So let me show you that. If you, this is our definition of Laplace transform. So if I want to find out, suppose this is f of s, correct? And then I can write out a e to the negative st dt 0 to infinity. What is the integral of this? A is outside, e to the negative st divided by negative s. Upper limit is infinity, lower limit is 0. So you do the same thing. A e to the negative s is outside the parenthesis, e to the negative infinity minus e to the 0. So this is like a in the parentheses. So 8 negative. This is 0. This is 1. So 0 minus 1 gives you a over s. So this is the same answer we got over here, correct? So I have shown you the basic method how to go from the time domain to the Laplace domain. So let's do one more Laplace example here for this one. Okay, let's do this for Laplace domain here. Laplace of a sine omega t. So for that, we know that e to the j omega t, Euler's theorem, and e to the negative j omega t. Why am I showing you? Because it is very convenient for me to convert it into the e to the exponent function, because our when you have f of t in terms of exponent function like e to the omega plus whatever it is, so then you do the um, integration easily rather than using sine omega t. So how would you eliminate cosine from here? You just take the negative here, correct? This is cancelled out. So you do the just a rearrangement and simplify the answer. So you see on the right hand side is 2j sine omega t, and left hand side e to the j omega t minus e to the negative j omega t. And then if you bring this 2j in the denominator, so sine omega t can be written from the Euler theorem. So now it is in the form of exponent. It is very convenient for us to use the formula. So let's use the formula here. Integral from 0 to infinity. Let's use this 1 over 2j outside. And this is suppose f of s e to the j omega t. Sorry, I forgot to write down e to the negative s. This is the Laplace transform definition, correct? So then you can do the math here. And did I have a over here? Yes, a is here. So I can write down a outside, correct? So this is my a. So you can write down a outside. So how about this? So if you do the math here, you will get a over 2j 1 over s minus j omega minus a over 2j 1 over s plus j omega. So finally, you can replace it by, let me show you this final word. How would you find out the what we call the LCM? Can you find out the LCM? A over 2j is outside minus, correct? So s is cancelled by this s, so you are left with 2j omega. So 2j is cancelled by this, you see. So I can write down here a omega over s square plus omega square. So the Laplace transform of a sine omega t can be written as this form. And similarly, you can prove by yourself that Laplace transform of a cosine using the Euler theorem. When you go home, you can use this one. Let me copy and paste it from the book chapter which I gave you. Then some more theorem. By definition, you can translate the function or delay it by a certain time. So let me grab this picture here. So if you have such a case that the time domain function is starting from 0, but it is now shifted by alpha delay. This is like t minus alpha means the function is delayed by alpha seconds or microsecond, whatever the unit, it doesn't matter. So, and 1 t minus alpha, this is telling us that it is delayed. But if this is rightly starting over here, so t minus 0 or t 1 sub t means it is right at the origin. So in that case, if you want to apply the property, Laplace property for the delayed function, so you would do the math. I can show you here. This is the Laplace transform property for the delayed function, that you just multiply this e to the negative as and f of s. Suppose, for example, you just did like sine omega t minus 2. So what is the Laplace transform? So you don't need to do every integration every time. You know that the Laplace transform of we know that Laplace transform of sine omega t equals to omega over s square plus omega square, and then it is delayed. So you would write it down, this one e to the, how much delay it is, negative 2s. correct? And then let me rewrite here. This is s, correct? And then you will write down the Laplace transform of the sine function. This delay, you have to write it down according to the Laplace transform property of the translation. Another thing I want to mention here, how do you take the Laplace transform of a pulse function and impulse function? So the way you can see that a pulse function, if you take a look, this is a unit step upward, and then over here it is unit step downward. If you add these two steps, you get a pulse function, correct? So what is the step value? What is the Laplace transform of the first a over t0? You will tell me, Professor, this is a over t0, 1 over s. Agreed? This value is little smaller, but this is given here. How about it has been delayed by t0? So the Laplace transform of a over t0, which has been delayed by this function. So you can write down the Laplace transform a over t naught s and e to the negative t naught s. Then when you add these to, oh sorry, this should be negative sign because this is going down with a similar scalar value, correct? Negative, yes, negative. So if you have a negative sign here, if you take the sum, combine them, combine two Laplace transform, combine 1 and 2. Let me show you the final answer here. So when you add these two functions together, these are two pieces of the unit step function, correct? So when you add them, you get this Laplace transform of the pulse function. We call this as a pulse function. So what if you want to reduce this t naught to 0? That if you bring it closer to uh, right at the origin, like an impulse, like if you hammer something, what is the time response? So if you make the limit t not equal to 0, so let's do this over here. If you want to limit this function, then you will apply the L'Hopital rule to the pulse function. The same pulse function, but now t naught is going to limit to 0. But when you bring it 0, 0 in the numerator, 0 in the denominator, you have to apply the L'Hopital rules to apply the limits, time derivative in the numerator. And for this one, you get either negative s, t naught into negative s. This is s, sorry, this is not t naught, this is s. So now you can apply this over here. This is correct. Negative, negative becomes positive. So a now you apply the time t equals to 0 here. So now you can get this one. the time derivative of this function. This is 0 minus e to the negative s. So this becomes 0 then divided by s. So then you have in the numerator a. You can study this. And there is another function, the Laplace transform of a impulse. This is a Laplace transform of impulse with magnitude a. So now if the magnitude is not a, different scalar, so you will see the impulse can be shown as for unity it will be 1. Another property you can see that if your function has been multiplied by the exponent e to the negative alpha t, so you will take the Laplace transform, add that variable alpha. For example, Laplace transform e to the negative a t times sine omega t. So you see the property says if you have multiplication of e to the negative at, you will take the same Laplace transform, but now this s needs to be added by the alpha term. So can I, this is my alpha. So can I just replace this by s plus alpha. So I'm going to replace this. In place of s, you plug in s plus alpha whole square. This is the right answer for the Laplace transform. This is a very useful formula to solve some of the response, time response. Another important definition is the differential equations. Please note down this formula for finding the Laplace transform of time derivative of first order. And for the second order or second derivative of the function, you get this answer. There is another formula which is important known as the final value theorem. So what is the final value theorem? That you might need it to see very quickly that if you plug in time limit infinity in the time domain, the answer which you get is the final value theorem. Or in the frequency domain, it becomes 0. As you know that frequency is equal to 1 over t. So if the time is infinity, frequency would be 0. But make sure you put f of s for the. And what is initial value theorem? That in place of t rather than infinity, you plug in time t equals to 0. But when you plug in time t equals to 0 over here, 0 plus means coming to the from the right hand side. Then infinite, this becomes 0 plus means coming from the right hand side of the function. So let me show you the difference here. So let's see. If you are measuring 0 plus means coming from the right hand side to pick up the value at the location 0, and if you're coming from the left hand side it is 0 minus. And you can see there is a sudden discontinuity, like sudden rise. For a step function there is a sudden rise here, but here if I take the sinusoidal function there is no discontinuity here. The f0 plus and f0 minus, they are meeting at a location, so you will see the same value here. The final thing which I want to share with you is, yes, this page, inverse Laplace transform. And for this inverse Laplace transform, I'm going to share with you some video lectures which you will watch at home. I think that's the end for the lecture.